Deep in space, gravity acts on vast clouds of dilute cosmic gas, pulling them relentlessly inward. As this material condenses, pressure climbs to extreme levels. When that gravitational pressure reaches a critical threshold, it forces hydrogen atoms to slam together. This ignition triggers continuous nuclear fusion, converting hydrogen directly into helium. The intense heat generated by this nuclear furnace strips electrons away from their atomic nuclei. The fuel pushes past the properties of a normal gas and enters a hyper-energized state known as plasma. At the exact moment of ignition, a star's entire evolutionary destiny is written. Every phase of its existence is dictated by one single variable, its initial mass. This self-regulating plasma engine remains highly stratified throughout its existence, locked in a perpetual battle to push energy outward against the crushing force of its own gravity. Every stellar engine eventually runs out of fuel, resulting in one of two endpoints. The star will either survive as a small, dormant white dwarf, or it will collapse into a black hole singularity. The specific path a star takes toward death is a strict mathematical certainty, governed entirely by the mass it started with. In 1930, the physicist Subramanian Chandrasekhar calculated the exact mathematical threshold that separates these two stellar death pathways. By mapping these strict mass thresholds, we can deduce the physical rules governing all stars and use those rules to deconstruct the specific internal plasma architecture of our own sun. Mass dictates both the duration the fusion engine can run and the precise physical nature of the corpse it leaves behind in the dark. As a star depletes its primary hydrogen fuel, the core contracts, forcing the outer layers to expand massively into a red giant phase. What happens next depends on the limit Chandrasekhar defined. That critical threshold is exactly 1.44 times the total mass of our sun. For stars that fall below this 1.44 threshold, the evolutionary path is quiet. These sublimit stars eventually shed their outer gaseous layers into space. They leave behind only their compressed, exposed core, known as a white dwarf, a glowing, hyper-dense fossil. Stripped of active fusion, the white dwarf slowly radiates away its residual heat over trillions of years, eventually dimming into a cold, hypothetical black dwarf. Stars under the Chandrasekhar limit die without catastrophic violence. Their gravity is too weak to crush their own atomic structures, preserving their cores as fading monuments. The physics change violently for stars possessing an initial mass greater than 1.44 solar masses. Inside these superlimit stars, gravitational pressure is so intense that it forces a severe chemical shift. Light elements like carbon are crushed and rapidly fused into heavy, dense materials like iron. The sudden accumulation of iron causes a catastrophic structural failure. The core implodes, and the rebounding shockwave blasts the star apart in a supernova explosion. In the immediate aftermath, the remaining core is crushed down into an ultra-dense sphere composed entirely of neutrons, a neutron star. Some of these hyper-compressed neutron stars rotate hundreds of times per second, becoming pulsars that sweep the cosmos with intense electromagnetic radio waves. There is one final threshold. If the surviving core exceeds a mass greater than 3 times our sun, the inward pressure overwhelms even the neutrons. The core collapses entirely into a black hole. Past the Chandrasekhar limit, gravity ceases to be a stabilizing force. It becomes an unstoppable mechanism that crushes matter out of existence. Our own sun serves as the clearest case study of a sublimit star. With a total lifespan of approximately 15 billion years, it has been running its fusion engine for about 5 billion years so far. This cross-section diagram maps the sun's highly structured internal anatomy. At the very center lies the core. Operating at 15 million degrees Celsius, this dense plasma zone is where hydrogen fuses into helium. Surrounding the core is the radiative zone. Here, energy generated by fusion escapes outward purely through electromagnetic radiation, traveling as high-frequency X-rays and gamma rays. Above that sits the convection zone. In this outer layer, energy transfers mechanically. Inside the convection zone, cells of hydrogen gas absorb heat from below and rise. As they near the surface, they cool and sink back down, forming a continuous mechanical loop. The interior of our star is a rigorously stratified system, designed by gravity and pressure to transport immense thermal energy from the core out to the void. Looking at the right hemisphere, we find the photosphere. This is the visible boundary layer of the Sun, operating at a comparatively cool 6,000 degrees Celsius. Immediately above lies the chromosphere. Here, the temperature abruptly spikes, jumping to 324,000 degrees Celsius. Finally, the outermost atmospheric layer is the corona. In this diffuse band of plasma, temperatures inexplicably reach 2.7 million degrees Celsius. The corona's faint, wispy structure is entirely washed out by the photosphere's light under normal conditions. It can only be observed from Earth during a total solar eclipse. Occasionally, localized pockets of extreme high-energy plasma overcome the Sun's gravitational hold. These solar flares tear through the atmosphere and erupt into the solar system. The Sun's outer layers present a thermodynamic anomaly. The atmosphere gets hotter the further it moves away from the core, creating a highly volatile boundary. Examining the surface texture on this diagram again reveals small, dark blemishes labeled sunspots. These are areas where the photosphere is anomalously cool. Sunspots are the result of intense, localized magnetic arcs breaking through the surface. These magnetic fields physically suppress the normal mechanical convection of heat from below. This graph tracks the strict 11-year sunspot cycle. Over a decade, these magnetic anomalies systematically migrate away from the equator, moving incrementally up to 40 degrees of latitude. This internal magnetic rhythm dictates the frequency and intensity of solar flares that manage to escape the Sun's gravity and travel toward Earth. When these highly charged particles strike our planet, they trigger communication disruptions and can produce a low-frequency atmospheric acoustic phenomenon known as Valser. As the solar particles collide with Earth's magnetic field, they ionize atmospheric gases, creating the vibrant light displays of the auroras, Borealis in the north and Australis in the south. These terrestrial impacts demonstrate that Earth resides within the extended active atmosphere of the solar engine, directly tethered to its internal magnetic pulses. The Sun is a highly stratified, volatile system, driven by its mass. Yet, its 11-year internal magnetic cycle and specific plasma layers only describe its localized behavior. When we zoom out to the scale of the Milky Way, our solar system is reduced to a microscopic point riding along one of the outer spiral arms. From this macro perspective, our entire solar system is hurtling through space, locked in an orbit traveling at 250 kilometers per second. At that velocity, it takes the Sun 250 million years to complete a single orbit, a duration classified as a cosmic year. The anchor for this immense rotation is the dense galactic bulge, containing billions of stars and massive black holes. The micro-forces of gravity crushing hydrogen inside the Sun's core are identical to the macro-forces of gravity pulling entire solar systems around the center of the galaxy. And the supermassive black holes providing that central gravitational anchor were forged by the exact same mass-deterministic limits calculated by Chandrasekhar. The universe operates with strict mechanical consistency. The precise thermodynamic equations that dictate the birth, internal plasma architecture, and death of a single star are the exact same laws orchestrating the rotation of a 100 billion star galaxy.